Everything you see around you, your phone, the chair you're sitting in, even you, it's all made of these impossibly tiny building blocks called atoms. But how in the world do you draw a picture of something you can't even see? Well, today, we're going to look at a game-changing model that gave us our very first real peek into that invisible universe. Yeah, that's the million-dollar question, isn't it? For the longest time, it was a total mystery. So let's dive into the model that finally cracked the code and honestly changed the world of chemistry forever. So our story really starts with a puzzle. Scientists, they knew the basic ingredients of an atom, but they just couldn't figure out how all the parts fit together. It was like having all the pieces of a jigsaw puzzle, but no picture on the box. Then, one scientist came along with an idea that made everything click into place. Okay, so before 1913, the picture of the atom was fuzzy, to say the least. Everyone kind of agreed there was a dense little center called the nucleus, and these things called electrons buzzing around it. But how, where, it was anybody's guess. And then, a Danish physicist named Niels Bohr steps onto the scene and brings this incredible new clarity to the whole thing. So, what was Bohr's big idea? Well, he basically said, hey, what if the electrons aren't just randomly swarming around like angry bees? He proposed that they were locked into specific, defined paths, kind of like planets orbiting the sun. He called these paths energy levels, and let me tell you, this idea was a total game changer. So, how does this whole model actually work? To really get Bohr's vision, we first need a super quick refresher on the three tiny particles that make up, well, every single atom. All right, here's our cast of characters. In the center, all packed together in the nucleus, you've got your positive protons and your neutral neutrons. Then, whizzing around on the outside in those energy levels we just talked about are the negative electrons. And it's the arrangement of those electrons that Bohr's model explains so perfectly. This is where it gets really cool. Bohr used this amazing analogy to explain his idea. He said, just imagine the atom is like a tiny solar system. The heavy nucleus, that's the sun, right in the middle. And the electrons? They're the planets, each one stuck in its own special orbit. It's a simple idea, but it makes this super complex concept instantly make sense. Now, this is a really, really important point. While that solar system idea is fantastic for getting the picture in your head, it is a simplification. In reality, electrons are a lot weirder than planets. But as a tool for understanding the basics, this model is absolutely brilliant. So these orbits have a proper name. We call them energy levels, or sometimes shells. And it's not a free-for-all out there. Nope, there are very strict rules about how many electrons can hang out in each shell. Think of it like assigned seating at a concert. You can't just sit anywhere you want. And here are the rules of the house. The first shell, that's the one right up close to the nucleus, can only hold 2 electrons, max. Once that one's full, you move to the second shell, which can hold up to 8. After that, the third shell and also hold 8. The most important thing to remember is they always fill up from the inside out. You gotta take the best seats first. All right, enough theory. We have the blueprint, we have the rules, so let's actually build something. We are going to put together an atom that's absolutely essential for life as we know it: carbon. Now, to build a carbon atom, we only need one little piece of information: its atomic number. And for carbon, that number is 6. That single number tells us everything we need to know. It's like this secret key. So what does atomic number 6 actually mean? It's super simple. It's just the number of protons in the nucleus. And in a neutral atom, the positive charges have to be balanced by negative charges. So 6 protons means we also have 6 electrons to play with. Okay, you ready? Let's place those 6 electrons. We follow the rules. Step 1, the first shell can hold 2. So boom, we put 2 of our 6 electrons there. That shell is now totally full. Step 2, how many do we have left? 4. So those remaining 4 electrons go into the next available space, the second shell. And there you have it. We just built a carbon atom. Now, see those 4 electrons we put in that outermost shell? They have a special name. They're called valence electrons. And these guys are the rock stars of chemistry. Seriously, they're the ones that reach out and interact with other atoms, forming the bonds that create literally everything, from water to you. For carbon, having 4 of them is what makes it the backbone of all life. Okay, so we know how atoms are built. But what happens when that structure gets a little energized? It turns out the Bohr model also explains something absolutely spectacular.
where bright, vivid colors come from. And it all comes down to electrons on the move.
This is where things get really dynamic. If you pump energy into an atom, let's say you heat it up, an electron can actually absorb that energy and jump to a higher, more distant energy level. It's like it just drank a double espresso and has a sudden burst of energy. But here's the thing, that high energy state is unstable. The electron can't stay up there forever, and what goes up must come down. So eventually, it's going to fall back down to its original comfortable home shell. And right here, this is the magic moment. As that electron falls back down, it has to get rid of that extra energy it absorbed. So how does it do it? It shoots it out as a tiny packet of light. That's it. That is literally how matter creates light. And this isn't some abstract concept. You've seen this your entire life. Those incredible, brilliant colors in a fireworks display, that's just different kinds of atoms getting heated up with their electrons jumping up and falling down, releasing light of different colors. It's the exact same thing that makes a neon sign glow that iconic red.
So, let's wrap this up. Why does this simple little solar system model matter so much? Because it gives us a clear way to picture how electrons are arranged. It introduces us to those all-important valence electrons, which are the key to chemical bonding. It even explains how atoms can create light and energy. And because of all that, it helps scientists predict how all the different elements are going to behave.
And that's really the big takeaway here. The world of the atom isn't just random chaos. It's a world filled with elegant, predictable rules. The Bohr model, even though it's a simplification, was our first real window into that world, allowing us to finally see the beautiful order that governs everything around us.